So in the last lecture, we saw that it was possible to pick the eigenvalues of the closed-loop system in such a way that they became equal to some desired eigenvalues for the particular case of the point mass robot. Now, today I want to be a little bit more general in terms of how do we go about doing this for arbitrary linear systems. And again, the whole idea here is that we pick our control gains such that the actual eigenvalues of the closed-loop system become equal to the desired eigenvalues. So this is the whole idea or philosophy behind this approach. So let's say that the characteristic equation associated with my closed-loop system, so this is, again, the determinant of lambda times I minus A minus BK. That's what this equation here says. Well, let's assume that if I compute this, I get the following expression. Well, what I now do is I pick my favorite eigenvalues, what I would like, and in this case, the lambda i's are my favorite eigenvalues. So what I have is an actual characteristic equation, which is this thing, and one that I would have had indeed the eigenvalues been equal to my favorite eigenvalues. And all I do now is line up the coefficients. So I take bn minus 1 has to be equal to an minus 1. Now, I'm writing an minus 1 as a function of k because it really is. K is the control knob or the control gain that we have to solve these n equations for. So this is the general procedure. And it seems magic. It seems that we can control anything. So the first question we should ask is this always possible? The second question is, well, where do these desired eigenvalues come from? And the third is, you know what, determinants are not that fun to compute. 2 by 2, fine, but when we go to higher order systems, it becomes a pain. Now, the first answer is, unfortunately, this isn't magic. We can't always do it. So what we need to understand is, in fact, when we can do it and when we cannot do it. The answer to the other question is, unfortunately, there isn't a recipe book that says, here are the eigenvalues you need to use. In fact, it's a little bit of an art and science, and the design choices that we make ultimately boil down to the choices of eigenvalues. So we have to discuss a little bit about how we pick our eigenvalues. Now, luckily for us, as answer to the third question, we don't have to actually compute this. In MATLAB, we can very easily use something called the place command. So if I have my A and B matrices, and I write down a vector of my favorite eigenvalues, then I simply run k is equal to place A, B, and P to compute this k matrix that gives us the desired eigenvalues. Cool. Okay, let's do some examples. Here is x dot is whatever x plus whatever u. These are two arbitrary A and B matrices. Well, we're going to have to pick a k. And again, k in this case has to be 1 by 2. And the reason we see that is that A is 2 by 2, B is 2 by 1. That means that k has to be 1 by 2 because these guys have to be the same. They cancel out. And what I end up with has to be of the right dimension. So that's why k in this situation has to be a 1 by 2 matrix. So if I compute this, I get the following matrix. Well, here is the characteristic equation, or this determinant. This should be equal to 0, but we're actually not going to solve it. All we're going to do is we're going to compute this determinant. And again, the way you compute determinants is this times this minus this times this. And if you do that, in this particular case, you get the following equation. Here is one coefficient that we're going to have to mess with. And here's the other coefficient that we're going to have to mess with. Cool. So, moving on, this is our characteristic equation. Let's say, again, for the sake of argument, that we want to place both our eigenvalues in -1. Then this is what we would have had this been indeed true. So now what I have to solve is these two being equal and these being equal. Those are the equations that we are forced to solve. So if we do that, first of all, for the coefficients in front of lambda, then we get that, after a while, k1 plus k2 is equal to 5. Well, let's look at the coefficients in front of lambda to the power 0, which means no lambdas. If we do that, we get k1 plus k2 equals to 1. Hey, wait a second. This is trouble, isn't it? K1 plus K2 is equal to 5, and K1 plus K2 is equal to 1. This doesn't seem all that promising. In fact, it's impossible. It can't be two things at the same time. So here, all of a sudden, we failed. We can't actually solve this. And what's really at play here is a lack of something called controllability. And controllability is this key term that describes if we have enough influence or control authority over our system. And when I said that it's not always possible to do pole placement, this is exactly what I meant. If we don't have enough control authority, we can't do anything. In fact, you can do nothing in that case. You just have to hope for the best or hold your nose. But we'll talk about that in a little bit later. So for now, this is what can go wrong. Lack of controllability. We don't know what controllability is yet, but that's something that we need to be aware of. Now, let's pretend that we could do it, though. How do we pick the eigenvalues? Well, it's not clear, like I said, but some things we should keep in mind is, well, if the eigenvalues have a non-zero imaginary part, right? Well, first of all, let's say that sigma plus j omega is an eigenvalue. Then there has to be another eigenvalue. In this case, I called it lambda j. There has to be another one that is the complex conjugate pair of this, because eigenvalues have to show up in complex conjugate pairs if indeed they are complex. So that's the first thing that we should keep in mind, that we can't just assign one complex eigenvalue. We have to assign two if that's the case. The other thing is, of course, we need the real part of the eigenvalues to be strictly negative, because otherwise we don't have asymptotic stability. The other thing to know is that if indeed we keep an imaginary part around, we get oscillations. So oscillations, if that's something we would like, typically we don't, but so if we don't like oscillations, the eigenvalues we pick are all real. If we're, for some reason, wanting oscillations, then we have to introduce imaginary parts. And the last thing is that the choice of eigenvalues actually affect the rate of convergence, meaning how quickly the system is stabilized. And in fact, the rate of convergence is dominated by the smallest eigenvalue. So let's say that I've actually picked a bunch of eigenvalues here. I've done pole placement, so here are my eigenvalues, my lambdas, and they happen to be here, 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 and here in the complex plane. Notice here that here I have a complex conjugate pair. Well, the eigenvalue that's closest to the imaginary axis is the smallest eigenvalue. And this eigenvalue actually dominates the performance in terms of how quickly the thing converges. So what you could do is if you make all your eigenvalues equal to minus a million, then you have a really, 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 really fast system. The problem is that if you make them really, really, really fast, you get really large control signals, which means that any physical actuator is going to saturate. So you don't want it to go super fast, because then you're saturating the actuators. So instead, what you need to do is somehow play around with these things to balance a little bit how fast or how slow you want your systems to be versus what the size of the control signal should be. So let's investigate these few concepts a little bit. And we're going to do it in MATLAB. So I've picked some system matrices randomly. So these are my system matrices. And then I picked some poles or eigenvalues. In this case, I picked a complex conjugate pair, minus 0.5 plus minus j, which you have to write as 1i in MATLAB. And then I run pole placement, case, place, ABP. And then all I do is I compute the solutions. So instead of me chit-chatting about this, why don't we switch over to MATLAB here and actually see it happen. So here is the same piece of code that you just saw. This is the eigenvalues. And if we run this, we see that we have a system that slowly decays down to 0, possibly. But there are oscillations going on there, right? Clearly, because I have imaginary eigenvalues. Now, the real parts here, minus 0.1, they're determining how quickly the system is converging. So if I instead use this P matrix here, same imaginary part, but a larger negative real part, then I should get a oscillatory response, but faster. And if I do that, we see here what's happening. This is the new system. It's still oscillating, but it's quicker getting down to 0, which is what we would expect. Now, let's get rid of the oscillations altogether. So if I now pick two purely real eigenvalues, and in fact, the smallest one is negative 0.5, so that's going to determine how quickly we're moving. We run this, then bam, see here. No oscillations, we're decaying down to 0 quite nicely. But maybe we're thinking that this is a little bit too slow, so let's pick some other eigenvalues here. In fact, negative 5 and negative 4, this should be dramatically quicker. And if I do that, bam, I get this. Bam, very quickly down to 0, a tiny bit of overshoot, and then we're stabilizing. So this is how we're going to have to play around a little bit with the eigenvalues to get the system performance out that we're interested in. Next time, we're going to investigate a little bit more what exactly was it that broke when we couldn't place the eigenvalues the way we wanted.